All right, so in this section, we're going to be taking a look at limits as x approaches a particular value, not as x approaches infinity. So not end behavior, we're going to look at a specific point on the graph. And so they're using the letter L to represent limit, the value that it's equal to. So we're going to look at functions, so equations, function rules, and see what's happening to the graph as the x value gets closer and closer to a particular number. And they just call that a, but that could be any value. So as x approaches 7 or as x approaches 5. So instead of infinite limits, we're looking at what we would call a finite limit or approaching a particular number. So I'm going to show you a picture right away so we can talk about this. So say that blue graph is an example of a function. There's a point discontinuity on it, so we have a place where it's discontinuous. What we want to do is find, kind of compare what the value of the limit is versus the value of the function. So let's talk about a couple locations on the graph. So I want you to find on the graph f of 4. So if I go over to x equals 4 and up to the function, this would be the location that would be f of 4. And on this graph, f of 4, it looks like, is equal to a value of 2. So the value of the function at 4 is 2. Now, the limit as x approaches 4 of the function is what number is the graph or the equation approaching as x gets closer and closer to 4 on both sides. So if you trace along the graph, coming from the left and coming from the right, as x gets closer and closer to 4, so as we close in on 4 on the x-axis, what is the function itself closing in on? What is it approaching? And it looks like from both sides, it's closing in on that green dot. It's getting closer and closer to 4. So not only does it approach from each side of 4, but it actually or 2, I say 4, it's 2, it's getting closer and closer to 2, sorry. So it's not only approaching from both sides, it actually equals it. So the value of the function, f of 4, is actually equal to the limit at that location. And notice at that location, it is continuous there. There is no discontinuity. So when we talk about the limit, it's tracing on the graph the values of the function. What are they getting closer to as we get closer and closer to 4 from both sides? Now, I want you to see what's happening at the point of discontinuity, though, at 2. F of 2 on this graph does not exist. It's an open circle. It's a point discontinuity there, so it is discontinuous there. So point discontinuity. Now, when we look at the limit, though, even though the value of the function doesn't exist, the limit could exist. So let's take a peek and see what I'm talking about there. As x gets closer and closer to 2, so as you close into the value 2 on the x-axis, look at what the value of the function is doing. It's closing in on from both sides, approaching from both sides, converging on from both sides that open circle, which is at a height of 3. So the limit actually exists and equals 3. It's approaching 3 from both sides, but it doesn't actually equal it because there's a point discontinuity happening there. So the limit can exist even when the value of the function doesn't. So the limit just has to do with, is it approaching the same number from both sides? Now, on a graph that has discontinuities, that can have different effects. So say you have one of those step functions that we had before. If you're looking at the limit at where one of those steps are, it would be approaching one number from the left and a different number from the right. They're not approaching the same thing. That would be a limit that does not exist. So if it's not approaching the same value from both sides, the limit would not exist then at that particular value of a, whatever that was. So that a value that we were talking about before. So there definitely can be situations where they don't approach the same thing. Or what if you have an infinite discontinuity happening? So like the 1 over x graph, something like that. So if we have a picture like this and we're looking at the limit as x approaches 0 as I go from both sides. Well, one part of the graph is getting infinitely large, the other one's getting infinitely small. They're not approaching the same number from both sides if I trace. This one's going down, this one's going up. That would be a limit that does not exist as well if we were looking at that value at 0. So there are definitely graphs that don't approach the same number from both sides. Okay, so what are some that always do? Continuous functions, so things like parabolas, cubics, linears, all those wonderful things. The value of the limit is always equal to the value of the function. So going back to our previous picture, that would be like case A. At 4, the function is continuous there, so the limit and the function values were equal to one another. So for continuous functions, life is good. Whatever the value of the function is, the limit is equal to the same thing. So let's take a look at a couple that would look like that. At places of discontinuity, then we have issues. So the places where a graph is continuous, the function and the limit equal the same thing. Where it's discontinuous, we have to take a look because the value of the function doesn't exist. So we have to be careful that we're looking at the right locations. All right, so let's talk about the first one. This equation right here is quadratic. That means it's a parabola. Parabolas are continuous graphs. There's no excluded values. The domain of the function is all real numbers. So if you want to find the value of the limit, all you need to do is find the value of the function. So the limit as x approaches 2 of x squared minus 4x plus 1 would be equal to the value of the function f of 2. So all I need to do is find the value of that function. So I would substitute in 2 squared minus 4 times 2 plus 1, and I'll get my value of my function. So when I go through and do the arithmetic, looks like I would get negative 3. So the limit is equal to the value of the function, which would be negative 3. So my limit and the value of the function would be the same. So if you graph that equation, I just want you to get kind of the picture understanding of what's going on here. If you graph that equation, hello graphing calculator, time to wake up. All right, so we got x squared, just so we can see the picture, minus 4x, and we know it's a parabola, plus 1. If I look at my picture, I'm going to do a zoom 6 so I don't know what my window is here. What I'm talking about when I say the limit as x approaches 2, so as I get closer and closer to 2 on the x-axis, if I trace on my graph closer and closer from each side, it looks like I'm converging at that location. So they're both sides of the graph are going towards that same value, which happens to be negative 3. So that's the idea of that limit equaling the value of the function because it's continuous. So the limit equals if it's continuous. All right, let's take a look at the next one. So this is still a parabola. Some people maybe would write it 1/3 times x minus 2 squared. That's the same thing. It's just the a value. It's been vertically compressed a little bit. What would the limit be as x approaches 0? Well, this is a continuous function again. It's continuous at all values because it's a parabola. So the value of the limit is just equal to the value of the function. So I'm just going to substitute in my 0. It's going to be exactly the same as f of 0. So the limit equals the value of the function. So I'd have 1/3 times 4 or 4/3. So this graph would be getting closer and closer to 4/3. So the value of the function is equal to the value of the limit because it's continuous. So continuous functions are wonderful. That makes our life a lot easier to deal with. Okay, let's take a look at the next one. When we take a look at the next graph, and we think about what's happening for this one, we want to look at if I can find that value. Is it continuous at the value they're asking me? So if I just tried to substitute in a 4, I'd be dividing by 0. It's not defined there. So let's go ahead and take a look at what this graph is doing and see if we can come up with a limit, because I can't do the value of the function. I can't just plug in 4. It's not continuous there. So when it's not continuous, I have to take a look at finding the limits in other ways. So I want to get the graph approach here first and see what I think it's getting close to. So I'm going to go ahead and put this in. Make sure you use fraction bar with your grouping symbols to make sure we have everything we need here. So x minus 4. And let's see what this graph looks like. So we looked at some of these rational functions earlier in the year. It looks linear. It's very interesting. When we do a degree 2 divided by a degree 1, you actually get something that looks like a line. But if you actually go to your table and take a look, got to go back to 0 here. If you go to your table and see what's happening at x equals 4, it's going to say error. The value of the function is not defined because I know I can't put 4 in. So I want to see what's happening as it gets closer and closer to 4 from both sides. So I'm going to go back to my graph, and I'm just going to use my trace function. So it's starting at 0, 0, and I'm going to trace to the right here, and I want to see what happens as the x value. So look at the bottom of your screen. Look at x. It's at like 1 something now. As x gets closer and closer to 4, what do the y's look like they're getting closer to? So looks like I'm getting closer and closer to 8. And if you come from the other direction, I'm getting my cursor a little bit further, and you come back towards 4, for x, it looks like we're coming back towards 8. It looks like from either side it's getting closer and closer to 8. So how can I show that when I don't have a continuous function? So this is discontinuous at x equals 4. It's continuous literally everywhere else in the graph, but it's discontinuous at x equals 4. So I can't just plug the 4 in there. So what can I do? Well, let's see if we can simplify that expression. So I can actually factor the numerator, x minus 4, x plus 4. I can divide out my common factor. And then this limit would be equivalent to finding the limit as x approaches 4 of x plus 4. And if you look at the equation, does it look like x plus 4? Y-intercept's at 4, and the slope is 1, up 1 over 1. So that's the exact same equation. So it's just discontinuous at 4. So now I can actually evaluate that limit. I can put in the 4. So 4 plus 4, the limit would be 8. So the value that it's approaching on each side is 8. I know it can't equal 8. That's discontinuous there, but it's approaching 8 from both sides. So it's closing in on the same value. So if you have a situation where it's discontinuous, you have either point or infinite discontinuity, see if you can simplify the expression to be able to figure out what value it's approaching. I could see it on my graph. I could actually look at it and see what's happening, but I need to be able to show that algebraically as well. Okay, so take a look at the next one. We have a very similar situation. I can't put in 3. It's discontinuous at x equals 3. Now we talked about different kinds of discontinuity. If it's a point discontinuity, your limit is still going to exist. So let's see if it's a point discontinuity again without even graphing. So let's see if we can simplify that fraction at all. So when we factor, I'm going to try an x minus 3 and an x plus 1. That multiplies to negative 3, adds to 2. Beautiful. So I can reduce that. So if I graph this, it would actually look linear again. Would have a y-intercept at 1. And a slope of 1, but again, it would be discontinuous at 3. I would not be able just to plug in 3 in that original. But now to do my limit, I sure can. 3 plus 1 would be 4. So the limit that it's going towards, if you trace on the graph, would be a 4. So if it's discontinuous, we still have ways that we can deal with and be able to solve for those limits. All right, so let's take a look at this last one. I want you to see if you can figure out what the limit as x approaches 2 of x cubed minus 8 over x squared minus 4. Now again, it's discontinuous at the value I'm looking at. I cannot just plug in x equals 2. It's discontinuous there. It's a place of discontinuity. So if I graphed it, you could take a look and see what's happening on the picture so we can understand what this graph is looking like. So I'm going to go ahead and do that. So go back and clear that out. You can always take a look. It's really a good idea to think about what the graphs are telling you. So let's take a peek. Don't forget your parentheses so we can see what that looks like. All right, graph. Now, again, we get sort of a goofy looking thing. We have a slant asymptote, right? The degree in the top is 1 greater, so we have a slant asymptote. There is definitely an issue going on here. We have a vertical asymptote happening here, and that looks like it's at -2. And then let's go to our table and see what's happening. So there's also an error at +2. So if I go back, if I think about what my excluded values are, think about setting the denominator of this equal to 0. What makes that 0? It would be both plus or minus 2. So it's discontinuous at both of these places. And specifically the one I'm looking for is as x approaches 2, definitely discontinuous. But what kind of discontinuity? Well, at -2, it looks like there's a vertical asymptote. So vertical asymptote, can't spell, it's all good. So that's an infinite discontinuity. We talked about those earlier in the year. But what's happening at x equals 2 is very different. At x equals 2, if I go back to my graph, you can't even see it. If you zoomed in really close, you could actually see that there's pixels separating there. So if I just did like from 1 to 3 for my window, you can actually see a break in between there, which is kind of cool. I'm going to show you that really quick so you can see what I'm talking about. I think that'll be enough to be able to do it. You only see this one little piece of the graph. But see that little break, that little teeny tiny hole? That's your point discontinuity. So at x equals 2, it is still discontinuous. But vertical asymptotes versus point discontinuity give us different outcomes when we have to look at what's happening for our limit. If I asked you what was the limit as x approaches -2, where this vertical asymptote would be, it would be does not exist because part of the values are decreasing. The other half of the graph is increasing. This limit would not exist if I was asking you for -2. But I'm asking you for +2, which is right here. So as you trace on the graph, does it look like it's approaching the same location from both sides? And I sure think it does. So let's see if we can figure out what that would be. All right, so let's try this. Now, the last ones, we were trying to reduce and simplify the fraction. So that's what I'm going to try to do here as well. Denominator, not a big deal. That's difference of squares. On the top, that's a difference of cubes. So when we're factoring, sometimes we have to use different formulas. The cube formula looks like this. If it's a cubed minus b cubed, it's a minus b times a squared plus ab plus b squared. That's a formula. You can look it up. It's our difference of cubes formula. So for us, that would be x minus 2 then. What's being cubed? What's being cubed? First thing squared, product of the two, and then second thing squared. What does this allow us to do? Well, now I'm being able to simplify that fraction and take a look at what I have left. And I'm going to be able to substitute in now that 2. Now, notice I wouldn't, oops, that's supposed to be a 2, sorry. X plus 2 down there. So notice if I was trying to find the limit as x approaches -2, that still wouldn't have helped me, right? I would not have been able to plug it in -2. There's not a limit there. We wouldn't be able to evaluate that. But because it's at 2, the point discontinuity, my graph is actually approaching the same number from both sides, and we know the limit exists. So I just have to plug in my 2, because at this location, it is approaching the same number from both sides. So we have 4 plus, so it looks like 12 divided by 4. So we have a limit of 3. So when we take a look at these values, this idea of knowing if it's continuous is really critical. Being able to look at the graph and connect that with what it means for a limit. So it just has to be approaching the same number from both sides. So in many rational functions, we just have to be careful. Is it continuous where I'm looking for the limit? If it's not, what kind of discontinuity is it? If it's point, I'm probably going to be able to figure out a value for that limit. I just need to simplify first. So factor and reduce.